Trigonometry, the sine rule. The sine rule. Sometimes we want to work out missing sides and angles of a triangle when the triangle does not have a right angle in it. We cannot use ordinary trigonometry, but we do have two rules that we can use. One is called the sine rule and one is called the cosine rule. We're going to look at the sine rule. So, if we've got a triangle ABC, the first thing that we need to do is label the sides. The side opposite the vertex A is labelled little a. So BC is labelled A. The side opposite the corner B is labelled little b. So AC is equal to B. And the side opposite C is labelled little c. And so AB is equal to C. So the theorem states that side A over the sine of angle A is equal to side B over the sine of angle B, and it's equal to the side C over the sine of the angle C. Or we can say the sine of angle A over side A is equal to the sine of angle B over the side B, and that's equal to the sine of angle C over the side C. Now, to prove this, we need to draw a construction. We draw a line from C perpendicular to the line AB to meet AB at D. Now, we label the length CD as H. So to prove it, if we look at the triangle ACD and consider angle A, we have the opposite over the hypotenuse is the sine of the angle. So H over B is equal to the sine of A. In other words, H is equal to B times sine A. If we look at triangle CBD and consider angle B, again we have the sine of the angle is the opposite over the hypotenuse. So H over A is equal to the sine of B. In other words, H is equal to A sine B. Now we've got two equations that are equal to H, so we can combine them to eliminate H. H is equal to B sine A, and H is also equal to A sine B, so A sine B is equal to B sine A. Now if we divide both sides by sine A times sine B, we see that sine B cancels on the left-hand side and sine A cancels on the right-hand side. And that leaves us with A over sine A is equal to B over sine B. By a similar method, we can prove B over sine B is equal to C over sine C. And so we have A over sine A equals B over sine B equals C over sine C. Or, if we go back to the equation A sine B equals B sine A and divide both sides by AB, we have sine B over B equals sine A over A. And so we can write sine of angle A over side A equals sine of angle B over side B, and that's equal to sine of angle C over side C. That is the sine rule. Now, we can demonstrate that the sine rule is true by just drawing a random triangle. Suppose we have the triangle ABC and we measure the sides and the angles. We can measure the side A and we see, using a ruler, that its length is 8.0 centimetres, measured to the nearest millimetre. When we measure side B, we see that its length is 5.8 centimetres to the nearest millimetre. And when we measure side C, we find the length is 6.9 centimetres to the nearest millimetre. We can also measure the angles. When we measure the angle C, we see on a protractor that it comes to 57.0 degrees. When we measure angle A as accurately as we can, the angle is 77.4 degrees. And when we measure angle B, we find the angle is 44.8 degrees as accurately as we can measure it. Now, if we write down A over sine A, that will be 8.0 over the sine of 77.4, which is equal to 8.19, or rounding it off to one decimal place, 8.2. If we look at B over sine B, that's equal to 5.8 over the sine of 44.8 degrees, which is equal to 8.23, or rounding it off to one decimal place, that's 8.2. And if we look at C over sine C, that's 6.9 over the sine of 57.0 degrees, which is equal to 8.23, or rounding it off to one decimal place, that's 8.2. So we see that within the limits of the drawing accuracy, A over sine A is equal to B over sine B, which is equal to C over sine C, as they all come out to be 8.2 to one decimal place. Now, let's look at an example to see how we can use the sine theorem. In example 1, we're given a triangle ABC with the angle A equal to 48 degrees, the angle B equal to 38 degrees, and the side AC equal to 8.6 centimetres. We're asked to find the length of BC, which is labelled x. And to solve this, we're going to use the sine rule. That is, A over sine A equals B over sine B equals C over sine C. Now we have the angle A is 48 degrees, the side B is 8.6 centimetres, and the angle B is 38 degrees. So using A over sine A equals B over sine B, we have A over sine 48 degrees equals 8.6 over sine 38 degrees. If we multiply both sides by sine of 48 degrees, we have A equals 8.6 times sine of 48 degrees over the sine of 38 degrees. If we type that into a calculator, it gives us the answer 10.3807 and more terms. Rounding that off to one decimal place, we get A, which is equal to x, is 10.4 centimetres. Now let's look at a second example. In the diagram, we have a triangle ABC. The angle A is 37 degrees. The side BC is 11.4 centimetres and the side AC is 17.3 centimetres. We want to find the angle theta. Now again, to solve this, we're going to use the sine rule. But since we're trying to find a missing angle, we'll use it in the form sine A over A equals sine B over B, which is equal to sine C over C. And we have the side B is 17.3, the angle A is 37 degrees, and the side A is 11.4. The angle that we want is theta, and that's the angle B. So we have sine of B over B equals sine of A over A. So sine of theta over 17.3 equals sine of 37 over 11.4. If we multiply both sides by 17.3, we get sine of theta equals 17.3 times sine of 37, all divided by 11.4. Now, if we type that into a calculator, that gives us the sine of theta is equal to 0.91328. So theta is equal to the inverse sine of 0.91328. But for this, there are two possible values of theta within the range 0 and 180 degrees. When we type it into the calculator, we get the answer theta is equal to 65.962. But there is another answer, which is 180 minus theta, which is 114.037 degrees. If we look at the diagram, we see that the angle theta is actually an obtuse angle. It's bigger than 90 degrees. So the answer that we want is theta equals 114.037 degrees, or rounding it off to one decimal place, theta equals 114.0 degrees. So let's look at what's called the ambiguous case with the sine rule. In the last example, the sine formula gave two possible answers. This can happen when calculating an angle. Now we've had this before. Quadratic equations also usually have two possible solutions. Both are potentially correct, and it's necessary to choose the right one depending on the question. So let's have a look at an example. An obtuse angle triangle ABC has the angle BAC equal to 40 degrees, the side AB equal to 8 centimetres, and the side BC equal to 6 centimetres. Find the angle ACB. Well, one method of doing this is by construction. We start by drawing a base line. We label the end of the line A. Now we draw an angle of 40 degrees at A. We use a protractor to do this. We mark the angle, and then from A we draw a line 8 centimetres long, and the other end of the line we label as B. Now we open the compass to 6 centimetres and draw an arc at centre B to intersect the base. There are two intersection points that could be C. Now, in the first case, we can measure the angle ACB using a protractor. And find it's 59.2 degrees. Now this means the angle ABC is equal to 80.8 degrees because the angles in the triangle add up to 180 degrees, and we see the triangle is not obtuse. If we label the other intersection of the arc as C, we have an angle of 59.2 degrees again, but it means the angle ACB is 180 minus 59.2, which is 120.8 degrees. So the triangle we have is obtuse. So this is the answer that we want. The angle ACB is 120.8 degrees. Now if we solve the problem using the sine rule, we'd have sine A over A equals sine B over B, which is equal to sine C over C. In this case, the side C is equal to 8 centimetres, the angle A is 40 degrees, and the side A is 6 centimetres. So sine C over 8 is equal to sine 40 over 6. If we multiply both sides by 8, we get sine C equals 8 times sine 40 all over 6, which means sine C is equal to 0.85705. And if we take the inverse sine, we get C equals the inverse sine of 0.85705, which the calculator gives as C is equal to 58.986 degrees. But C could also be equal to 180 minus that. In other words, C is equal to 121.013 degrees. Now we want a triangle with an obtuse angle, so that means we must choose the angle ACB is equal to 121.0 degrees rounded off to one decimal place. So we see both methods give the same two answers within the accuracy of our drawing, and we have to choose which is the correct answer.